Hi, my name is Haghi-Tabrizi, and in this presentation, I'm going to be going over my implementation of an intersection management unit for autonomous vehicles. So an overview of this presentation, first I'm going to discuss the background and motivation for this research. Then I'm going to discuss the intersection management unit and all of its moving parts. And then I'm going to discuss my implementation of this intersection management unit in code. And then I'm going to demonstrate the performance of the code, evaluate it, discuss future improvements for this, and then go over a final conclusion. So a bit of background about this research, it is actually built upon research that was already being done and published by these two researchers. And the paper they published was Intersection Management for Autonomous Vehicles with Vehicle to Infrastructure Communication. And the problem they address is intersections, more specifically their inefficiencies, which cost time and money and pollute, leading to global warming. So the solution they proposed was using autonomous vehicles, as this would make the process more efficient and make the downfalls of intersections less impactful. And so the goal was to create an efficient intersection management system specifically designed for autonomous vehicles. And the only constraint about this research is that all the vehicles have to be fully autonomous and able to communicate with the intersection management unit. So the intersection management unit, or the IMU, is able to communicate with all of the autonomous vehicles that interact with the intersection. And its purpose is to manage all of these incoming vehicles and dictate when they can leave and enter the intersection. So with the IMU comes a conflict matrix. And this is just a 2D array showing which routes in the intersection conflict with each other. So in this intersection, there are 11 routes. And here we see, in this example, Route 1 and Route 7 do not interact with each other. So when we look at the conflict matrix in the R1 and the R7 section, it is 0 because these routes don't conflict. But looking at another example, Route 8 and Route 1 do conflict as they cross paths. So looking at the conflict matrix, a 1 is labeled between R1 and R8. Also with the IMU comes an information list, and this is just a list of all the vehicles that are interacting with the intersection, and this includes the vehicle's ID, the route the vehicle is taking, and the time until the vehicle leaves the intersection. So here's a flowchart of how the algorithm works. First, it detects if a vehicle arrives, and when it does, it checks the conflict matrix to see if there's a potential conflict. If there's no conflict, then it sends null to the vehicle, and the vehicle adjusts its speed and it estimates the leaving time to the intersection management unit. And then the intersection management unit updates all of their information lists, adds the car, and goes back to the wait state. But if there is a potential conflict after checking the conflict matrix, then the IMU sends back the maximum time the vehicle has to wait before entering. And then with that information, the vehicle can adjust its speed to that Tmax value, and then again sends its estimated leaving time to the IMU, and it logs that vehicle in the information list. So to implement this IMU, the Pygame library was used to display the intersection and all the car movement throughout it. And this is the main data structure used for the program. These are the main classes. There are some other ones that aren't as significant, but it all starts with the traffic simulation class, which includes things like the time, the IMU, which is also a separate class, and the car list, which is all the cars that are interacting with the intersection. And it's able to start the simulation and spawn cars and update. With a car, all the car has is its X position, its Y position, and the angle that it's driving at, and it also is able to print using the Pygame library. And with the intersection management unit, it has this confirmation matrix, its information list, which includes the vehicle information, and it's also able to go through its new vehicle protocols by reporting to the car the Tmax time, whether it's null or the car has to wait, and is able to check for conflicts and log new vehicles to the information list. And the information list is just a list of vehicle information, which includes the vehicle ID, route, and the time that the vehicle is leaving the intersection. So here's a demonstration of the intersection management unit at work. As soon as you click on this file, the display will show of the intersection, and vehicles will begin to spawn in. And we can see that the algorithm is successful in managing all of these vehicles to prevent any collisions or mishaps. And all these vehicles are able to travel through the intersection efficiently because of the intersection management unit. And all of the vehicles are spawned at random routes. And the spawn rate can be adjusted based on a vehicle traffic. And this simulation will continue spawning cars. And we can see that it is indeed successful in managing all of the vehicles at the same time. So evaluating the performance of that demonstration, we clearly saw that it was successful in managing all of the autonomous vehicles that interacted with the intersection. And we also saw that there were no mishaps or collision that took place. And there never will be based on this program because it's more so a proof of concept with everything going correctly. Whereas in real life, there are factors that are variable and can change. Like physical factors such as weather and vehicles not performing ideally. But because this is just a simulation and it does not consider those physical variables, no mishaps will take place because the algorithm is successful in preventing that. We also saw in some situations that the vehicles waited longer than they needed to, and this is coded into the algorithm, and it is designed that way. It is not the most efficient algorithm, but instead it is an algorithm that addresses the problem. Even the researchers that proposed this solution with the intersection management unit and its algorithm, they said that this was not the most efficient algorithm, but more so it is just a solution that addresses the problem, and it is much, much more efficient than the modern day traffic light solution to intersections. So the next steps for this research, the road will not have 100% autonomous vehicles for the near future, so some sort of autonomous vehicle and human driver coexistence has to be made. This could easily be implemented into the algorithm where a traffic light is implemented where human drivers can interact with that. But at the same time, the IMU is running and it's able to manage both the autonomous vehicles and the human drivers for a more efficient process than the one today. Also, the algorithm itself can become more efficient. One technique that the algorithm doesn't take use of is vehicle platooning, which sends multiple vehicles at the same time, and this could improve the efficiency. Also, one improvement that I thought of is instead of having a two-dimensional conflict matrix, there could be a three-dimensional conflict matrix that also considers the time that the routes would conflict, because routes only conflict for a specific time in that route. For the majority of that route of the intersection, the cars won't conflict with each other. It's just when the location of where their paths conflict. So by considering time, it could be much more efficient and cars wouldn't have to wait longer than they needed to. So in conclusion, autonomous vehicle algorithms are going to be a major focus with the rise of autonomous vehicles that are taking place in our society and driving on the road. And this intersection management unit algorithm, it provides a successful solution to that complex problem. It is not the most efficient solution as of now, and it can be built upon to become more efficient and better. Thank you for taking the time to listen, and this is the end of my presentation.